Okay, now the technical today it is mainly a technical lecture in which we behave as Lagrange taught us to behave. As an epigraph of this paper, I have chosen the same epigraph as Lagrange in Mécanique analytique, a preface. This epigraph is here. On trouvera point de figure dans cet ouvrage. You will not find any picture in this work. Les méthodes que j'y expose ne demandent ni construction, ni raisonnement géométrique ou mécanique, mais seulement des opérations algébriques assujetties à une marche régulière et uniforme. The methods which I am exposing here do not demand neither constructions nor geometrical or mechanical reasonings, but only algebraic operations which are subject to a regular and uniform procedure. Ceux qui aiment l'analyse verront avec plaisir la mécanique en devenir une nouvelle branche et me seront gré d'en avoir attendu ainsi le domaine. Those who love mathematical analysis will see with pleasure the mechanics to become a new branch of this theory, and they will be grateful to me because I have extended its domain in this way. Why it is important to say this now? Because every physical, this is what you have to understand, every physical reasoning is needed to write down the action. So you write down this action functional. Here you need to exert your creative vision of physical phenomena. Okay, so you need to invent an action functional basing your choice on some intuitive and not well rigorously defined reasonings. So you decide that for a reason or another, the correct action functional is a given one. This is what in the philosophy of science is called, with the German term, Ansatz, choice which is made as a conjecture without need to any justification except its consequences. So you write the action, then you stop conjecturing, and you must do a regular sequence of algebraic operations. And at the end of this regular sequence of algebraic operation, you get your equations of motion. So those presentations in which they start with a balance of something, then for physical reasons they add boundary conditions, then another physical reasoning gives you a constitutive equation, then you find a lack of mathematical consistency, then you add another term in another place. This way of proceeding after Lagrange is not anymore acceptable. The format of a mathematical theory for describing physical phenomena is this one. You postulate an action. If you have dissipation, you postulate Hamilton-Rayleigh dissipation potential. Then you do your sequence of algebraic operations, and you find your final result. So now on, we can be wrong only because we are doing some wrong calculation. What is a fluid? A fluid is something whose deformation energy is expressed in terms of an Eulerian density of deformation energy, and this Eulerian density depends on the Eulerian mass density, and if you are in second gradient theories, also on Eulerian gradient of mass density. Of course, grad rho is a vector. Okay? So we need to impose objectivity. The deformation energy does not depend on the observer. Two different observers measure the same deformation energy of a given fluid. Grad rho is a vector which is changing in components when you change the observer. So we need to find an objective dependence of deformation energy. This is a subject which we will treat all together in the next lectures. So I give you the final result. The final result is that the only possible observer invariant deformation energy for second gradient fluids is an energy in which two scalar quantities are the only one on which this deformation energy may depend. Mass density, which is clearly observer independent, and the square root of the norm of the gradient of rho, which we call beta. Okay. Now, in the literature, the deformation energy, which is studied by Kahn and Hilliard, actually they obtain it via some statistical mechanical reasonings. A similar energy is introduced by Korteweg, but it is better that we don't try to make the list of mistakes, errors, misunderstandings, approximations. We go straight to the treatment of the most general theory. But what I want to underline is that actually, in the framework of Lagrangian least action principle, to study the most general energy 56 and less general energy 57 is the same. You find exactly the same difficulties, technical difficulties. I will tell you more. As I wanted to be sure of my calculations, I said, let me treat 57, so I'm sure that I am able to obtain the correct result. Then I generalize the calculation. Okay, for a reason which I will try to make clear to you, calculating the first variation of 57 actually was more difficult than calculating the first variation of 56. So my calculations which I did in parallel, of 57, of the Euler-Lagrange equations starting from 57, became correct after those which I had written for 56. So once more, saving is not earning. The structure of equations are directing you towards the correct result. Because if you have a lambda which can be simplified, factorized, you lose the structure, the elegant structure of the equations. But in any case, I believe that there is no other paper in the literature, at least I could not find any other paper in the literature, in which the most general energy, 56, is studied in the detail I'm showing you. I found only 3 lines in a paper by Casal, 1962. Then nothing else. Okay, so you should not believe that we are doing impossible calculations. These calculations, which I will show you, have the same difficulty of the derivation using the chain rule of one function and the basic reasonings needed for proving Rouchet-Capelli theorem. So the algebra which is behind this is very, very simple. What is important is that when you write in Lagrangian description the deformation energy, you have a J, which is the determinant of F, which is needed there for changing the variable, passing from the Eulerian to the Lagrangian description, which, if you like, you can represent as rho naught, the referential mass density of the fluid, divided rho flag B, which is the mass density in the Eulerian description represented in the Lagrangian, composed with chi minus 1, to go back to Lagrangian description.
If I can interrupt you, now you are assuming that the material is homogeneous as a material. The fact that you have this rho zero, which is a constant. Otherwise, you would get the...
No, I try to simplify this in the presentation, but your question obliges me to tell you. No, your question is appropriate. And it was the subject of a violent controversy between Poisson and Piola.
So sorry, I'm up to date, so to speak.
Yeah. What has been proven by Piola is that you can, for every fluid, you can always choose a Lagrangian configuration in which rho naught is constant.
So you can prove that given this Eulerian density field, you can always map it back to a reference configuration where it is.
Actually, Piola calls Lagrangian configuration the reference configuration, and then he introduces an anterior auxiliary configuration, and he writes this action in these anterior auxiliary configurations, and he proves that this can be a configuration in which rho naught is constant.
It sounds strange.
It is strange because it is useless. Because actually, if you need only to prove that given a regular field of rho, you can find another regular field with a diffeomorphism in which rho is constant. which is Bianchi-Ricci theorem, in a sense, a trivial consequence of Bianchi-Ricci theorem.
So there is something concerning the structure of the space. I mean, this is standard.
But what is clever, for this reason I'm calling it Piola-Bianchi-Ricci identity. Piola, 50 years before, proved a particular case of this result for answering to Poisson, who claimed that this rho naught constant couldn't be chosen. Okay, so this is a very delicate point. Actually, a fluid is a material for which you can choose a Lagrangian description with rho naught constant in space. This could be a good definition of fluid. Okay? Yeah, very interesting. But, what is astonishing is that this is written in Piola's book and nobody knows. It's very clearly written. Okay, so actually, think about this. A fluid is a material for which you can find a Lagrangian referential description in which the mass density is constant. Okay? So you have to calculate the first variation of J times W cap capillary of rho and beta. By the way, the only person who is citing one every 2 pages Piola in the literature of continuum mechanics is Marsden, which is the inventor of this notation.
This is due to Marsden.
This is due to Marsden. And it is clear that Marsden knew the exact content of Piola's book. It could be interesting to discover how. Okay, so now you calculate the first variation of this, and the first variation of this is W cap times delta J, then dW cap over d rho J times delta rho, and dW cap over d beta J delta beta, which delta means the first variation. So you go ahead and you write the J over the F delta F, the rho over the F delta F. Then you remember that beta is grad rho. I will show you Eulerian grad rho. I will show you in a while that beta depends both on F and grad F. So here you have the beta over the F, delta F, plus the beta over the grad F, delta grad F. So, in order to calculate this equation, which is the equilibrium equation for a capillary fluid in Lagrangian configuration, this equation we found painfully integrating by parts in the last lecture, we need to calculate the W Eulerian, the F we have already calculated some lectures ago. Now we have to calculate dW cap over dF and dW cap over d grad F. So it is clear what we are doing. We have reduced what usually is presented as a series of assumptions coming out of the blue, which are added in the right moment without any true justification. Okay, we now have to painfully calculate some partial derivatives, which may be technically difficult, but not at all creative. You are not thinking anymore. A computer can do the same calculations. The creative action is postulating the action. Okay? Okay, now I close for a moment this document and we start calculating slowly. Of course, I give you the main features of the calculations, then you will be patient enough. We are talking about no more than 10 pages of calculations, which are strongly algorithmic. So you need simply to learn the rules, then you follow the calculations. I give you the some of the results which we need. Okay, the first result which we need, we already introduced and proved. When you have the determinant of a tensor, of a matrix, if you represent it in suitable basis, this partial derivative, the partial derivative of the determinant of A with respect to one of the entries of A is given by the determinant of A times the remark here that you have switched, because when you calculate the derivative with respect to a contravariant index, you get a covariant quantity. This I have proven for you in all details. And when you derive with respect to a covariant component, you get a contravariant component. So this equation tells you this. If you calculate the derivative of the determinant of a matrix with respect to one entry of this matrix, this partial derivative is equal to the determinant of the matrix times the component mi of the transpose of the inverse of the matrix you are considering. I think that this is the most important algebraic relationship in continuum mechanics. This is at the basis of every calculation. You start always from here. The partial derivatives of rho, j, f minus 1, and f with respect to f can be easily calculated if you know how to derive the determinant with respect to the entries. So something which I have learned by my professor of mathematical analysis first year is the following. Mathematics is not difficult. You need only a lot of patience. It is a pyramid. So if you look at this huge construction, you are frightened. You built it one small stone on another one. So you need simply to be patient and construct one piece after the other. There is nothing difficult. So rho, look at this equation. What is rho arrow b? It is rho naught determinant of f. This is the theorem of change of variables in integration. Okay, so when you need to calculate the derivative of rho with respect to f, you simply perform the derivation of j with respect to f and you get the result. In the previous step you have already calculated the derivative of the determinant, j is determinant of f. You calculate the derivative of determinant of f with respect to f, and at a final result you get this, which we already used and which we will need again. In order to show you the reason of the Marsden notation, rho is an Eulerian field. D rho B over df, it is a Lagrangian field. Okay, so you have to write rho f minus 1, which is defined in the Eulerian description, and you have to compose with k minus 1, forgetting inequality. Of course, you soon are bored by this heavy notation, but sometimes nobody explains you what is happening, and so you cannot understand. So the right behavior is Marsden 1. You write the first 50 pages of your book with this notation, then starting from a given moment, you say, now on I skip, when misunderstanding is not possible anymore. Because you have to understand that f is leaving Lagrangian, f minus 1 is leaving Eulerian, rho is leaving Eulerian. So you cannot equate an Eulerian field to a Lagrangian field. So you need to compose these fields for transporting one to another domain, or vice versa, the second to the first domain. Okay? The partial derivative of mass density with respect to the deformation matrix C we calculated already. The Lagrangian and Eulerian gradient of f minus 1 we don't need directly, so we skip. Here we start writing what we need. Rho, comma, small k. There is a famous piece of music which is entitled Invitation to Dance, which is very beautiful. This lecture is invitation to calculations. I cannot replace your exercise with a piece of paper and a pen doing these calculations. My strong suggestion is that you learn to do it. Okay? Also because what I said to you immediately is false. I need the f minus 1, the partial derivative, so we will go back immediately. Okay? So, we can skip it because I have another deduction which is possible without f minus 1. So as these calculations are full of small symbols, in order to avoid mistakes, I did it in parallel in two different ways all the time. So I'm sure that the result is correct. You have to learn to do this. This is essential. So rho comma k is equal to rho naught, determinant of f, arrow Eulerian, comma k. I hope that you know how to derive 1 over x. The derivative of 1 over x is minus 1 over x squared. Okay? So, using the derivative of composed functions, you get this step. Okay? These first two equalities you find as they are in Piola. I should change the denotation. That f in Piola is called h. So, what Piola is doing painfully, but we are very good and we do not need it, is calculating this derivative. So this derivative is what? Once more, is the derivative of that f with respect to f, which with the cofactor I have written here. And then you have the derivative of fh with respect to k. But as f minus 1 is the capital X with respect to the small x, using again, so this is the derivative of k minus 1, using again the derivative of composed functions, you get this result, which in a compact form can be written in this way, which is the one, actually is the one which we need. With this equation, it is evident beta is the square root of the norm of this gradient. Look, you have both f and grad f inside. So when you calculate the first variation of beta, you need to calculate the derivative of beta with respect to f and the derivative of beta with respect to grad f. So this is the reason for which in the previous formula I wrote these two derivatives. Okay. These are formulas which are equivalent to the previous one once you multiply left side times f minus 1 or times f on the right. Because we will need later grad rho divided rho in terms of f and its derivatives, either Lagrangian or Eulerian. So I remind you, comma, capital letter means the derivative with respect to the Lagrangian coordinates. Comma, small letter means the derivative with respect to the Eulerian coordinate. Okay? Okay. So, d rho b over df is simply d over df of this animal times grad f. Now, unfortunately, we need to stop to calculate this derivative. But look at the structure of what we are doing. Then you will check all details. Here I have the product of these three quantities, rho, f minus 1, f minus 1. And here I have the rho over df, this not derived, plus rho f, the derivative of this, plus rho f minus 1, the derivative of that. So there is nothing mysterious. Leibniz rule. Of course, we need this effort. So I need to go back and to show you this calculation. The idea is very easy. If you have a matrix F, and if the determinant of this matrix is different from 0, you can uniquely represent its inverse as a function of the entries of F. So here we have a very simple thing to do, to calculate the derivative of the C, capital C, small b element of f minus 1 with respect to the element f, L, m. So you have 9 scalar functions of 9 scalar variables. To make you understand why it is very important for you to learn tensor calculus, I tell you that Piola wrote explicitly all these 9 equations and did these calculations one after the other, which is a nightmare. Okay? I think there is a conservation of pain. You painfully must to learn a more abstract theory. When you have painfully obtained the mastering of this abstract theory, you save a lot of pain. So you earn, if you are using the theory, a number of times which is big enough. Okay? So let us go back. I wanted to show you, but I forgot to produce the PDF file, because this half page of calculations fill 10 pages of Piola's work. So you of course you could decide that everything we are doing is useless. Okay, but if you, for a reason, need the capillary equation, the equation for a capillary fluid, then you need tensor calculus. Of course, you could do another thing. You could decide that you come to me every time you need a new equation, and you pay me and I write for you the equations. This is a possibility which could be very pleasant.
This they need to do because all these things are filled up with small, tiny errors here and there that only you may know, and then they...
No, I tell you why. The reason for which there are four co-authors, one of which is Russian, is that we wanted to be sure that... but anyway, now you discover, once you are inside Levi-Civita notation, you discover that it is impossible to be wrong. Look here, MD, L saturated L. So in the left side, you need to have the same indices that you have on the right, and every index which is appearing on one side and is not appearing on the other side must be one time up, one time down. There is a mathematical package doing these calculations. This is an algorithmic structure of the tensor calculus. So even if you could believe that there is a set of dancing letters on the blackboard, actually there is a logic inside, and this logic is rather strict. Delta is Kronecker delta. So here I am writing that if you saturate one matrix with its inverse, you get identity. A remark that I could have written this with the identity Lagrangian. Here I've written it with the with the identity Eulerian. Here I've written with the Lagrangian identity. So I have always double checks of what I'm doing. Then I calculate the derivative of first and second member. The second member is constant. so its derivative is 0. The first member I derive using Leibniz rule. So I get comma C, comma C. I changed the order because I need it for technical reasons later. So this expression, remark, you have 0 here, MD free, C free, and L saturated. So this equality tells you that a given third order tensor has all components equal to 0. Okay? Then you can place this on the right side. You can multiply times F minus 1 di saturating D. Okay. This animal is delta small I small l. Okay, so this small l becomes I, and you get the derivative, you get F minus 1 comma C in terms of FLD comma C. Okay, and you can repeat this for Lagrangian, for Eulerian derivatives. Okay, similar reasoning is producing for you df minus 1 CB derived with respect to Fm. Because you use this identity and you derive left and right side with respect to FIC, capital F, small I, capital C. Okay? So what is telling you this formula? This formula is telling you that the derivative of F minus 1 CB with respect to FLM entry of the matrix F, which is a fourth order tensor, 2 times Eulerian covariant and 2 times Eulerian Lagrangian contravariant, is given in terms of F minus 1 matrix. Okay? So this is what we need in the calculations which we were performing here. So this derivative and this derivative here we now replace with the previously found results, and d rho over df we have already calculated. So by the way, I don't want to hide you that I'm using a semi-automatic calculation method, because I'm using Maple, which is inbuilt in scientific workplace, and I am copying the equations which I have deduced before and replacing inside, and some simplification I get with Maple when possible, or I'm doing it by hand, but I'm not doing any more calculations on a piece of paper. I'm doing all of them directly on the screen, which is easier because you don't need to copy by hands every time. You cut and paste. Of course, you have to be careful because one small error can be deadly. Okay, so at the end, d rho b over dFLM is given by this expression. Now, this expression is not suitable to be expressed in the Eulerian representation because you have all f minus 1, f. So we go back to this 37 and you get this simple formula in which you get rho comma b, rho comma l, rho, and the derivative of f with respect to the Lagrangian coordinates. Now we have 35, which is one of the derivatives which we have learned to calculate before when we did the standard trick starting from there. Instead of having the Lagrangian derivative, we have the Eulerian derivative. And we get this very compact formula with two terms only. So we are able to get the derivative of beta. So I tell you the reason for which the opposers of Lagrange hate this method is that you need to be patient. But the great advantage is that your physical assumptions are done only one time at the beginning. Then everything is calculus. So do you know that the derivative of the grad rho dot grad rho is 2 times grad rho inner product the grad rho over df, and similarly for the grad f. These formulas are standard, the derivative of the square of an inner product. So the beta over df is equal to grad rho times the derivative which I have previously calculated, which is written here. So we are already on the end of the calculations. We are very close to get our Lagrangian equation of evolution. Okay? Now, when 3 years ago I accepted the challenge to give a talk in this field, which I believed to be my own field, the field of my PhD thesis, I didn't know that nowhere in the literature the Lagrangian equations for capillary fluids was not written anywhere. With a trick, which I already told you, the trick which is ideologically very misleading, because in the literature, in the PhD thesis of Pierre Seppecher, for instance, he postulates the principle of virtual works in the Eulerian description. He adds in the Eulerian description the balance of energy, And then he gets the Eulerian evolution equations, which, by the way, are not well posed, because you need to tell that grad rho comes from a displacement. I mean, rho, a density, is rho naught determinant of f, where f is the gradient of something. If you write directly the Eulerian equations with a field rho, you are not assured that this is true. And if you add the velocity v, you are not assured that this velocity is the derivative of k with respect to time. So the Lagrangian version of your equations are needed if you want to be sure to have some well-posed equations. Okay. Okay. To derive the beta over df is trivial because grad rho, because FIHK appears linearly in the rho over in rho comma b. So let's go back. If you go to our expression here, this one, this is the gradient of f with respect to Lagrangian coordinates. And this animal is linear in this gradient. So you can calculate the derivative immediately. It is the coefficient of this f. Okay? So you don't need any other calculation for getting this final result, which is very easy and compact. So we now go back to the other file. So the beta over df, it is here. So dw over df, we can, this animal, we know. This animal we have calculated. This animal we have calculated now. So we simply replace inside. Now I want to tell you why using the particular case is very dangerous. Because when W cap is lambda half beta, dw over d beta is lambda half times 2, it is lambda half, okay? And this animal times beta is again W cap. So in all calculations, you mixed W cap and this quantity, and you lose the control of what you are doing. While if you stay general, W cap plus JW cap over D rho gives you a generalized pressure, which we can call P cap, while this animal stays there and cannot be mixed with the spherical part of stress. Okay. Now, the trick for saving painful calculations is to define a Piola stress. This trick is very evident if you look at this structure. You have div sounding minus div sounding. So it is very natural to define sounding minus div this animal. So dw cap over df minus divergence of dw cap over d grad f, and to call this animal a Piola stress, which has exactly the same structure as the Piola stress which we already introduced in the Euler fluids. However, because it is one-time contravariant in the Lagrangian and one-time covariant in the Eulerian description. However, it depends on the derivatives which we have painfully calculated up to now. So, if you go and replace inside the expressions the calculated d beta over df, this is pure calculation, you get this Piola stress. I think that Piola could see this equation would be very happy, because he writes for alpha page how important is to recognize the presence of this structure in the Lagrangian equation. You have j f minus 1, j f minus 1, j f minus 1. So tensor calculus allows you to immediately spot the right terms which you need. So the Piola stress is this animal which is a delta Eulerian delta Kronecker delta times jf minus 1, and then you have, look here, you have rho comma alpha, rho comma I, which is the free index here, and then you have the saturation of this animal with L, which saturates with rho. So this is a shear term. This is a spherical term. So we have divergence, Eulerian divergence of this animal plus the terms coming from Euler equations equal mass times acceleration. So we have a well-posed set of equations governing the motion of a capillary fluid in Lagrangian coordinates. Now, a fluid dynamicist could say, I don't believe that this is the standard equations which I have seen written in Canillard or somewhere else. Okay, the calculations are ended, so I simply need to remind you something which we already have discussed. The Piola transformation for divergence. We already discussed when we needed to transform the equations of Euler fluids from Lagrange configuration to Euler configuration. If you have divergence of something in the Lagrangian description, this divergence becomes the divergence of J F minus transposed that tensor in the new configuration. In the calculations which I needed to perform, I needed a particular case of this equation when the field T is constant. When the field T is constant, this derivative is 0. This, of course, you can choose more than constant. You can choose the identity. Okay, so here you have that TA. Okay, I have to be careful, because T is a vector, is a linear map which applies vectors from one configuration to the other. So what it means, identity? We have to be very careful. We assume that both Lagrangian and Eulerian configuration have space of displacements, so the set of vectors representing displacements can be identified with a translation, with a suitable translation. So in this way we can take formula 9 and we can, so actually this is not identity. If we consider for T, capital A, small a, the rigid displacement of a vector from Lagrangian configuration to Eulerian one. So this is what is called parallel transport. What is astonishing is that Piola uses this parallel transport because from Piola equality number 9 applied with parallel transport T, he gets divergence of J F minus transpose equal to 0. That is, the derivative of J F minus 1 A J with respect to capital X A equals 0. If you do these quick calculations, you get this magic formula. Take a displacement key. Consider the mass density rho which you are producing with this displacement. Calculate its gradient in the Eulerian representation. Divide it times rho. Well, you get F minus 1 derived with respect to Lagrangian variable. This equation found by Piola is expressing the fact that the curvature of Eulerian configuration and Lagrangian configuration are both 0. This is Bianchi-Ricci condition for being flat for a three-dimensional manifold.
Are there any application in which you do not have this flat conditions? I mean,
In general relativity, to my knowledge.
no, yeah, of course, but I mean in classical mechanics or continuous.
Shell theories. Shell.
Yeah, but then because there is a variety in itself, which is
Because you have a Gaussian set of coordinates with respect to which you represent constitutive equations. So you have a curved manifold which has a physical meaning. It is the configuration where your shell is, for instance, stress-free. Then you need to consider non-flat manifolds in classical mechanics. Okay, so.
But then things like related to the fact that you may have a body which is subject to some thermodynamic deformation due to heat fluxes, to thermal stresses, things like that are still embedded on this, or you have to go to the non-flat things?
I don't want, I must be honest, I didn't study literature in this aspect. I strongly suspect you are right. I do not know if yours is a conjecture or we should be proven with suitable research, or if somebody already developed a theory of heat-induced or temperature-induced deformations which can be described with curvature in the three-dimensional manifold. This is, I agree with you, there should be something important inside here, but I do not know if there is something or not. I will check. We have to check. This is a clever possibility. I think that in this way, so-called heat-imposed deformation or residual stresses can be studied. I'm sure about this. I tried to do something in this, but I wrote only one paper and I'm not happy of it. It is difficult, very difficult. Okay, so the rule for transforming a Piola tensor into a Cauchy tensor in general is this one. You take the Piola tensor, then you saturate with f-1 every Eulerian index to get the Lagrangian index, and you have J in front of it. By the way, this formula tells you that the power expressed in Lagrangian representation is equal to the power expressed in, or work expressed in, the Eulerian representation. So, what is stress? Is a tensor which multiplied the gradient of velocity gives you the power of internal work. Cauchy stress is doing this work in the Eulerian configuration. Piola stress is doing this work in the Lagrangian configuration. How you are jumping from Piola to Cauchy? J f-1, suitably saturating the indices. So this parenthesis, which is repeating what we already did, will allow us to conclude our painful derivation. But believe me, we did all the job in 1 month, being lazy. I mean, I needed the Russian precision for placing all commas at the right place, okay? But look, J minus 1 Piola F equal Cauchy. Look how elegant. You saturate the capital letter and you get a purely Eulerian animal. The Cauchy stress tensor for capillary fluid is minus P cap plus rho, this Eulerian divergence. This is wrong, this is small g here. Look, the powerful of the denotation is that you immediately discover the mistake, and here, as announced, you have shear, non-spherical stress. The divergence of this animal gives you the extra term to be added to Euler equation of fluids. So you calculate this divergence. Here I'm overwriting the calculations, and you get this beautiful balance equation for generalized cannulate fluids. No, this is for cannulate fluids, because this is the particular case of lambda. So, what we know at the end of these painful calculations? You have this term, which is the standard one. When you can neglect this, you have Stokes' assumption. This is the material derivative. This is the gradient of pressure. These are body forces. Here you have lambda, which is the capillary constant, rho times the gradient of Laplacian of rho. Okay? Never a Laplacian operator appeared in a more suitable place, because this equation allows you to a continuum description, to get a continuum description of a fluid in which Laplace formula for pressure holds. So let us spend a few minutes for discussing this. Imagine lambda equal 0. Imagine the velocity field V equals 0, and imagine there is no body forces. Possible. What you get? Gradient of P equals 0. So P equal constant. So how can you imagine to describe with this model the equilibrium of a drop in presence of its vapor? It is or you have a capillary tube and you have the capillary surge of a fluid. So how you can describe this? It is impossible, because you have one phase having a pressure which is higher than the pressure in the other phase. So look how beautiful is this method. You conjecture that there is a long-range interaction, so you have a deformation energy which is not depending only on rho, but it is depending also on grad rho. So one particle of fluid with a given density has a content of energy which is different if the closed particle has the same energy or same density, or if the closed particle has a slightly higher density. So you have a system in which varying gradients of density gives you an extra content of energy. This is a conjecture which you can base on many physical reasoning, from statistical mechanics, whatever you want. Okay? You start with this conjecture. You do 10 pages of calculations, at the end of which you discover that gradient of P plus, okay, it's not exactly like that. You have gradient of P plus lambda rho gradient of Laplacian of rho is equal to 0. So you get that for suitable boundary conditions, you can have a region with one rho, a region with another value of rho, and a boundary layer in which you have a varying gradient, so a non-vanishing Laplacian, and you can have equilibrium with this varying field of density. So in principle you can have drops with a higher pressure with respect to surrounding vapor. Of course, now you can get this very easily with half an hour of COMSOL or 1 day of COMSOL. In 1995, I needed 6 months of painful numerical integrations.
I have a curiosity over here.
Yeah.
I mean, if you start from the equation above, a little bit over, you have this divergence of the Cauchy stress.
Yes. You want to see the general one?
No. I'm just wondering about it. You made all these calculations, and then it happens that you get the rho in front of the derivative, right?
Yes.
So you start from something which is in divergence form, and you end up with something a little bit
nearly similar to gradient.
Yes. But of course, the starting point, the general one, is the divergence of the...
Yeah, but this is true also for this.
General case, yes.
So shear belongs to a particular class.
No, my point was, assume you have given the right-hand side of the last equation, the one in which you have the rho in front of the gradient.
This one.
This one. Then, recognizing that this one can be written in divergence form is not trivial at all.
No. And for this reason, somebody told me that it was difficult to find the Lagrangian form of capillary fluids, because with some tricks, I mean, I told you already, they got directly this equation. So they couldn't see how I could get this as the divergence of something.
Yeah.
Doing the calculations simple, lengthy but simple.
You get that right.
Yeah. Now, just for telling you why my research, and possibly the one in common with Professor Casciola, is directed towards this subject. We want to study the vibration of a drop in equilibrium with its vapor. It is very painful to get anything from this Eulerian form. because you need to add balance of mass, and still the problem is not well posed. Because you need to tell somehow to the equations that there is a displacement key whose grad space gradient determinant gives you rho and whose time derivative gives key. Instead, look at Piola structure. Piola, you get the divergence, the Lagrangian divergence of this animal, and you have JF minus 1 in front of everything. So you know that key is existing.
You know, another interesting point is that if you go back to that equation you were showing before, if you try to derive this from, say, a molecular modeling of your fluid, it's sort of rather simple to get at something that looks the one you have the row outside there.
This one?
And that one. I mean, you end up with rather straightforwardly with something which is not in conservative form. If you want to go to that one, you have to employ the tricks conceived by Kirkwood, Irving, and that guys, which is, I mean, sort of complex, I mean, formally. And also in that case, I mean, you can end up with something which is hardly recognized as a divergence.
But I don't know now to which statistical mechanical deduction you are referring. However, in Casal-Guin 1985, I think, it is proven that a deduction made by Korteweg, another deduction made later by Kahn, Hilliard, Hahn, Allen, were missing some energetically important terms.
No, I mean, I'm just meaning some straightforward calculation. You start from the Liouville equation and you integrate out degrees of freedom. I mean.
Yeah, but then you add a grand canonical assumption. You do some trick.
No, you don't need that. I mean, just take the distribution function. I mean, the general one.
But for averaging, you need to do something. You average the microscopic system somehow.
Yeah, you just what you're doing is that you just go to what they call the reduced distribution function for a single particle. So you integrate out the n-1 guys and keep on just formally. You don't need to.
Okay, so you are doing some tricks which may not preserve, for instance, energy conservation.
I mean, you don't do nothing violent.
Okay, so this is another deduction.
Something that Kirkwood and Irving,
they got it for capillary fluid?
No, they got completely general. Then if you look at cases in which you may have...
so they get no local interactions?
There are, yes.
Okay, so this is another story.
But it's purely formal. I mean, you do not end up with having something closed.
Okay. Of course, it is very clever, in my opinion, to know which target macroscopic theory you have in mind, and then you start from micro theories and you do suitable assumption for getting your target theory, and in this way you get a macro identification. Okay, but this is a story which maybe we will discuss in another lecture. Okay, so I think that for today we can stop.